Imagine a world painted in rust and dust. This is Mars, a planet of profound silence and immense desolate beauty. Its sky is a pale pinkish orange, a stark contrast to our own familiar blue. Winds howl across vast plains, kicking up global dust storms that can shroud the entire world for weeks. These are not gentle breezes. They are planetary-scale events, reshaping the landscape with every gust. We look at this world, our celestial neighbor, and we see a story written in its canyons and craters, a story of a dynamic past and a mysterious present. What secrets are buried beneath that thin, cold air? What whispers are carried on those alien winds? This is a world that invites us to dream, to wonder. For centuries we have gazed at its reddish hue in our night sky. We have imagined canals, cities, and civilizations. Science has since painted a more realistic yet no less captivating picture. A world of towering volcanoes like Olympus Mons, so vast it would dwarf any mountain on Earth. A world with a canyon system, Valles Marineris, that stretches as far as the entire United States. This is a place of extremes, of epic scales. It is a world that has lost much, but perhaps not everything. We send our robotic emissaries, our rovers and orbiters to listen to this whisper. We are on a quest to answer one of the oldest questions we have ever asked. Are we alone? The story of water on Mars is a dramatic tale of planetary transformation. Billions of years ago, Mars was a different world. It was warmer, it was wetter. Evidence is etched all over its surface. We see ancient river deltas fanning out just as they do on Earth. We see meandering channels carved by flowing water. We see shorelines of vast, long-vanished lakes and oceans. These are not illusions. They are the geological scars of a world that once had a thick atmosphere, a gentle climate, and abundant liquid water. A world that might have been, for a time, a cradle for life. Where did all that water go? Some of it escaped into space, stripped away over eons as Mars lost its protective magnetic field. The solar wind, a relentless stream of charged particles from the sun, slowly eroded the Martian atmosphere. But much of that ancient water is still there. It is frozen. It is locked away in the planet's polar ice caps, vast sheets of water ice mixed with frozen carbon dioxide. And most excitingly, it is likely buried underground. Our rovers have found direct evidence of this watery past. They have discovered minerals like hematite and gypsum, which on Earth form almost exclusively in the presence of water. They have drilled into rocks that were clearly altered by liquid flowing through them long ago. So the search for life on Mars has shifted. We now look down. We look for places where that subsurface water might still exist in a liquid state. This is where Martian life, if it ever existed, might have made its last stand. A hidden biosphere, just waiting to be discovered. Let us now journey farther out into the solar system, past the asteroid belt to the realm of the gas giants. Here, orbiting the colossal planet Jupiter, is a moon called Europa. From a distance it looks like a marbled white and brown sphere, a cosmic ornament. It is smooth, uncannily so. It lacks the heavy cratering you see on our own moon and on Mercury. Something is constantly resurfacing Europa, wiping its slate clean. That something, we believe, is a dynamic shifting crust of ice. A shell of frozen water, perhaps miles thick. This icy shell is not a placid, unbroken surface. It is a tangled web of cracks and ridges. Long, dark lines crisscross the globe, some stretching for thousands of miles. These features, called lineae, look like scars. They tell a story of a world under stress, pulled and stretched by the immense gravity of Jupiter. As Europa orbits, it is constantly flexed and squeezed. This tidal flexing generates heat. It warms the moon's interior, it churns the ice, it creates the vast network of fractures we see today. It is a world in motion. What lies beneath this fractured crust of ice? The evidence points to something extraordinary. A global ocean of liquid salt water, an ocean that could contain more than twice the water in all of Earth's oceans combined. This isn't just a guess. The Hubble Space Telescope has captured apparent plumes of water vapor, geysers shooting high into the vacuum of space, originating from the moon's warmer, cracked regions. These plumes are a direct message from the hidden sea below. Imagine that, an alien ocean locked away beneath a shield of ice, protected from the intense radiation that bombards Jupiter's system, warmed not by a distant sun but by the relentless pull of a giant planet. This changes everything. The habitable zone might be much larger than we thought. Life might not need sunlight. It could arise in the dark, cold depths of space, powered by chemistry and planetary heat. Europa presents us with a new paradigm for where to look for life. Because on Earth, wherever we find liquid water, we find life. Even in the most extreme environments, in the crushing pressure and total darkness of our deepest ocean trenches, life thrives. Around hydrothermal vents, volcanic fissures on the seafloor that spew superheated mineral-rich water, entire ecosystems exist. These ecosystems don't rely on sunlight for energy. This is the model for life on Europa. Now we travel even farther from the sun to the majestic ringed planet, Saturn. Here we find another small icy moon that has completely upended our understanding of where life might be found. This is Enceladus. At first glance it appears to be a tiny, bright white snowball in space. It is one of the most reflective objects in our solar system, but this little moon holds a spectacular secret. In 2005, the Cassini spacecraft made a startling discovery as it flew past Enceladus's south pole. It saw jets of ice and water vapor erupting from the surface and shooting hundreds of miles into space. These are not small trickles. They are colossal geysers, plumes of icy particles, water vapor, simple organic molecules blasting out from a series of long, parallel cracks in the ice. These cracks, nicknamed tiger stripes, are warmer than the surrounding terrain. They are the source of a constant, powerful eruption. Enceladus is actively venting the contents of its interior out into space. Cassini was able to fly directly through these plumes, sampling their composition. It was like the moon was offering us a free sample of what lies beneath its frozen crust. The discovery of these geysers was a game-changer. It confirmed that Enceladus, like Europa, has a subsurface ocean of liquid water. But unlike Europa, where the ocean is buried under miles of thick ice, the ocean on Enceladus is much more accessible. The tiger stripes are a direct connection to the liquid water below. The pressure from within forces this water up through the cracks and out into space. This tiny moon, only about 310 miles in diameter, is a geologically active world. What Cassini found in those plumes was even more astounding. It detected water vapor ice particles, salts, a variety of organic molecules. It found methane, carbon dioxide, ammonia. Even more compelling, it detected molecular hydrogen. On Earth, molecular hydrogen is a fantastic source of food for certain types of microbes. Its presence in the plumes of Enceladus strongly suggests that there are hydrothermal vents on the floor of its ocean, similar to what we hypothesize for Europa. It's a flashing neon sign that says, the chemistry for life is happening here. The plumes of Enceladus offer an unprecedented opportunity. We don't have to design a multi-billion-dollar lander that can drill through miles of ice to get a sample of the ocean. Enceladus is doing the hard work for us. It is ejecting samples of its ocean into space, where we can simply fly a spacecraft through and collect them. This makes Enceladus one of the easiest places in the solar system to search for signs of life. A future mission could be designed with sophisticated instruments, specifically to look for the complex organic molecules that are the telltale signatures of biological processes. What are we looking for, exactly? We are looking for biosignatures, amino acids, lipids, specific ratios of isotopes, patterns in the complexity of molecules, chemical fingerprints that life leaves behind, a signal in the noise of non-biological chemistry. Enceladus is not just a maybe, it is a prime suspect, a world that demands a closer look. What does it take to make life? When we search for life on other worlds, we are guided by the only example we have, life on Earth. And from that single data point, we have distilled a basic recipe, a list of ingredients that seem to be essential. The first and most important ingredient is liquid water. Water is a universal solvent. It can dissolve and transport chemicals, allowing them to interact and form more complex molecules. It provides a medium in which the chemistry of life can happen. This is why our search is so focused on following the water. The second ingredient is a source of energy. Life is an active process. It requires energy to build things, to move, to reproduce. On Earth, most life gets its energy from the sun through photosynthesis. But as we've seen, that's not the only way. Life can also get energy from chemistry, from the chemical reactions between rocks and water powered by a planet's internal heat. This is the kind of energy source we expect to find on worlds like Europa and Enceladus. It's a more universal form of energy, one that doesn't depend on proximity to a star. The third ingredient is a set of essential chemical elements. Life on Earth is primarily built from 6 elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon is the star of the show. It is incredibly versatile. It can form long, complex chains and rings, creating the backbone for the vast array of organic molecules that life uses. These elements are common throughout the universe. They are forged in the hearts of stars and scattered across the cosmos. Mars may have had all 3 in its past and might still have them in hidden pockets today. Europa and Enceladus almost certainly have all three right now in their subsurface oceans. We stand on a cosmic shoreline looking out at a vast, unexplored ocean. For most of human history, that ocean was just a collection of glittering lights in the night sky. Now, we are building ships to sail that ocean. Our robotic probes are the first tentative voyages away from our home port. They have shown us that the ocean is dotted with islands, Mars, Europa, Enceladus, worlds that are far more complex and interesting than we ever dreamed. Worlds of red deserts, hidden seas, icy geysers, chemical promise, each one a potential harbor for life. This quest is about more than just finding alien microbes, it is about understanding our own place in the universe. Are we a fluke, a beautiful but lonely accident in an otherwise sterile cosmos? Or is life a common, perhaps even inevitable outcome of the laws of physics and chemistry? Is the universe teeming with life, from the simple to the complex? Finding even the simplest microbe on Mars would begin to answer that question. Finding even the simplest microbe on Europa would begin to answer that question. It would tell us that the spark of life can ignite on more than one world, that we are part of a larger cosmic biology. The search requires patience, it requires persistence, it requires a commitment to science and exploration. There will be setbacks, but we will keep going, because we are a curious species. The journey has just begun, and the universe awaits.